Right, morning guys. Today we're going to look at exothermic and endothermic reactions. Now you should find on Insight a copy of this here sheet, and this is the summary really. So these are all the notes you need, and as we go through the lesson, if you can fill those in, that'd be spectacular, because that's really all you need to know at the time being. You will notice this is chemistry, not biology, and the reason is I'm picking up the back end of that from Mrs. Evans. We've pretty much finished the biology. There is a section we haven't done, but we'll come back to that later, and I'll explain why later on. So let's kick off. Really, what are exothermic and endothermic reactions? Right. All chemical reactions involve energy changes in thermal energy. Now, if you think in terms of physics, in terms of energy stores, energy is transferred from one place to another, and chemicals have lots of stored energy called chemical energy. It's stored in their bonds. So if there's a change in energy which gives out heat, that's called an exothermic reaction, and it comes from the word exo meaning exit, therm meaning heat, thermal energy. If you think of a door you walk out of, it's an exit. If you think of the book of the Bible where the Israelites leave Egypt, that's called Exodus. That's where the word comes from. Okay, X for out. So it gives out heat. The opposite of an exit is an entrance. So if a chemical reaction takes in heat energy and stores that as chemical energy, we would call that an endothermic reaction. They get cold. They will feel cold to the touch. So N as an entrance. Now, endothermic reactions are rare. The reason they're rare is because they appear to break one of the laws of thermodynamics. Now they don't, but that's an A-level kind of topic, but they appear to, because one of the laws of thermodynamics is heat will go from hot to cold. So if a reaction's got lots of heat energy, it will release that to the surroundings. There are reasons why some don't, but we won't go into that today. So most reactions are exothermic. So because they're the most common ones, we can give loads of examples of those. So exothermic reactions release thermal energy. They give out heat. What that means is if you're next to an exothermic reaction, you will feel that as an increase in temperature. You will feel the heat coming off it. So there's loads of examples. Combustion is an example. You burn something, it gives out thermal energy. Respiration. If you go for a run, you're going to be hot at the end of that, because respiration is an exothermic process. Most chemical reactions are exothermic. So we neutralise an acid with an alkali, it'll give out heat energy. Metals and acids, most chemical reactions. The thermite process is what that picture is there. That's a specific example of that. When we're all back in school, I might show you that reaction because it's a good example of an exothermic reaction. So let's have a look at an example of this. This is a metal and an acid. So if we actually look at that reaction there, what will take place? So you start off, you measure the temperature of the acid. This, by the way, is something we would have done practically if we were in school. Unfortunately, we're not able to do that remotely. If you chuck in a bit of acid, you'll see bubbles of hydrogen coming off that as it reacts. It'll react to make magnesium chloride and hydrogen. And if you look at that over time, the temperature goes up as chemical energy is transferred into thermal energy. It gives out heat. So there's an increase in temperature. Because there's an increase in temperature, the energy in the system has gone down. The energy stored in the chemical bonds has gone down, but there's a change in temperature, which is a raise in thermal energy. So think of it in terms of energy stores. Chemical energy store goes down, thermal energy store goes up. Where's the thermal energy store? That's in the surroundings. So it's the surroundings that increase in temperature. In this case, the surroundings are the water the reaction is taking place in, and the thermometer, the temperature probe. Okay, so if it goes up in temperature, if there's an increase in temperature, that means that it's exothermic. Okay, so chemical energy is converted to thermal energy. That causes the temperature of the mixture, of the surroundings, to rise. If you put your hands next to it, you are the surroundings. It will feel hot to the touch, or warm to the touch anyway. If you leave it, it's going to cool down again. I've got a cup of tea sitting here, which I made before, and it's starting to cool down. Why? Because thermal energy in there is slowly being dissipated into the surroundings, so it is cooling down. Excuse me. Oh, right. Now, we look at that graphically. What we can see is that at the start, the reactants have got lots of energy. That's chemical energy. And what happens to that chemical energy store is, as thermal energy is given out, that means the energy store's gone down because it's gone somewhere else. That energy is released. That means that the products have less energy than the reactants. This arrow here, you can sort of imagine, is the amount of energy that's released. Imagine an arrow coming off that, which is the thermal energy being released from the system. So there's a change in energy. We call that change in energy delta H. Delta is like a Greek capital D. It's a triangle. H is for enthalpy or thermal energy. It's a physics term primarily. So there's a change in energy in the system because the reactant's chemical energy store has gone down. Why? Because the thermal energy store of the surroundings has gone up. So the energy change is negative. We say delta H is negative. So exothermic reactions release thermal energy. So the temperature of the surroundings goes up, so it feels hot to the touch. The energy change is negative because the products have less energy than the reactants. So hopefully you'll be able to fill this in. So this is the summary there. If you want to pause the video and have a quick look and make sure you've done all of those, I'm going to put the answers up in a second. So pause now. Okay, answers now then. Hopefully you've done it. Whoops. Solve. There we go. So exothermic reactions release energy. Any example you could have written, combustion is the one there, but it doesn't matter. The temperature of the surroundings will increase. That's because thermal energy is released to the surroundings. In an exothermic reaction, the reactants have more energy than the products. So delta H, or the energy change, is negative. Right, exothermic reactions common. Why? Because that's laws of thermodynamics, energy going out. Right. Endothermic reactions, what's the difference here then? So endothermic reactions absorb thermal energy. So they cause a decrease in temperature. If you put your hand next to a block of ice, the block of ice feels cold. Why? Because thermal energy from your hand, is the store of thermal energy in your hand, is being transferred to break or overcome the bonds in the solid ice to melt it. So it feels cold to the touch because your thermal energy store is being transferred into there to do something. Now that's a change of state. That's not a chemical reaction, but the point still stands. So what examples have we got? Well, thermal decomposition is an example. Thermal decomposition, you put energy in to make it break down. One quite obvious one is photosynthesis. Photosynthesis, as we've done in biology, is the exact opposite of respiration. Respiration is exothermic. So that means the exact opposite of that must be endothermic. Photosynthesis needs energy from the sun for the reaction to take place. That energy is then released by respiration later on. So photosynthesis is endothermic. It's taking in energy from the sun. Electrolysis is an example. Electrolysis is where we split up compounds back to their elements using electricity. You've got to put energy in, electrical energy in, so that is endothermic. It's taking in energy. Okay, sherbet is another example. If you've ever had sherbet, it's got a cooling effect on the tongue. That's because an endothermic reaction takes place between the citric acid and the sodium bicarbonate. So that's a sort of one of the feelings of sherbet. It cools the tongue. It's also got sugar in there to be sweet, and that reaction is fizzy. That's why we eat stuff. Right. So here's an example of an endothermic reaction. So here's ammonium nitrate in water. It's quite a rare example. We don't do too many endothermic reactions, but you start off at 20 degrees. In goes, I've lost my mouse pointer. There it is. In goes the ammonium nitrate. And as that dissolves, that forms ammonium and nitrate ions, and you'll see a decrease in temperature. That temperature is going down. Why? Because the surroundings, the water and the temperature probe are the surroundings. Thermal energy from them is being converted into chemical energy. So think about the energy stores. The thermal energy store is the surroundings, the chemical energy store is in the chemicals, and so thermal energy is being converted into chemical energy. Okay, so that will cool down. Because there is a decrease in temperature, the reaction is endothermic. So that's a decrease in the temperature of the surroundings. I know I keep banging on about that, but that's quite an important distinction. Right, so what happens is thermal energy in the reaction mixture is converted to chemical energy in the products. And the reaction mixture, we're thinking in terms of the water, we're thinking in terms of the surroundings. The test tube will feel cold. If you put your hands next to it, it will feel cold. It's stealing thermal energy from your hand. So thermal energy is transferred to the reaction mixture and it cools. If you leave it, it'll warm up again. It's going to equilibrate back at room temperature eventually. Same as my hot cup of tea will cool to room temperature if I leave it long enough. If I've got a nice cold drink, that would increase in temperature to room temperature if I leave it long enough. So let's think in terms of the energy change for this reaction here. If you want to pause this and have a quick think about what it's going to look like before I press play. Okay, right, let's see what you came up with. So this time, the reactants have less energy than the products. So the reactants have a fixed amount of energy, they always do, because that's the amount of chemical bonds they have. This time, the products have more energy than the reactants. They have a bigger chemical energy store. The chemical bonds are trapping more energy or storing more energy. Where's that energy come from? It's come from the surroundings. So if you imagine an arrow coming in, that's thermal energy being taken into that system. So there's an energy change, or delta H. This time delta H is positive because they've got more energy at the end than they had at the start. Endothermic reactions absorb thermal energy. The energy change is positive. Okay, right. So just to finish off, this is the last little bit, second half of your fill in the blanks sheet. So again, if you want to pause it and have a quick look at those answers, and I'll go through them in a second. Okay, so first ones then, endothermic reactions absorb energy. In an endothermic reaction, and you could pick any. Personally, I'd have gone with photosynthesis because it's one you've learned in quite a lot of detail, but there's the one on the sheet, ammonium nitrate and water. The temperature will decrease. Why? This is because heat, thermal energy is taken in from the surroundings, and that means that the reactants have less energy than the products. They have less energy than the products because the products have a greater chemical energy store than the reactants had. Where's that energy change come from? Where's that energy transfer taking place? Because the thermal energy store of the surroundings has decreased and the chemical energy store of the products has increased by the same amount. Okay, so nearly there now, guys. Main difference with endothermic reactions, they're rare. Why? Because they have to take in heat energy. They increase in thermal energy and they feel cold when you touch them. That is not particularly common. We'll look at why it's not particularly common in a little bit more detail next time. But just quickly, some reactions are reversible. Reversible reactions are reactions where the products can react back to reform the original reactants, and all of them are exothermic in one direction and endothermic in the other. So if a reaction takes in heat going one way, it'll give out heat going the other way. And because you're going in exactly the same, or from the same reactant to the same product and vice versa, the energy change is equal and opposite. So if it takes in, for example, I don't know, 200 kilojoules of energy per mole, it'll give out 200 kilojoules per energy per mole. So endothermic reactions and exothermic reactions are in reversible reactions are equal and opposite. Right. Make sure you fill the sheet in. Please keep it for your notes. I'll ping out the answers later. Don't worry about sending it to me, but if you have any questions, you know where to find me, crumb@tahs.net. Otherwise, guys, have a great weekend, and I'll see you all next time.